Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about the following topic: inferences about linear functions of our simple linear regression model. Okay? Okay, so we have two objectives for this video. One, we would like to find a test statistic to carry out hypothesis tests. Okay, and we would like to find a formula, an expression, to compute confidence intervals. Well, now before I actually show you what we mean by a linear function of the parameters, let's specify which model we are going to be using to derive this test statistic and then that formula for our confidence interval. Okay, so let me write down the model that we are considering here. It turns out, and that's why in the past we have discussed the centered model, because it turns out that it will be easier to derive that test statistic and that formula for a confidence interval if we do it using a centered model. So that's the one that we're going to be using here. Okay, yi equals beta 0 plus beta 1 times xi, the value of the predictor variable for that particular observation, minus x bar. So that's what we mean, remember, by a centered model. And we have played around with that guy before. Okay, epsilon I, that random fluctuation, the error term. Okay, that's the model. Now let's talk about the assumptions. Okay, so clearly, if we take the expected value, right, and we take into account the assumptions that we usually make about the distribution of the errors, right, that the errors are normally distributed with mean 0 and variance sigma square, and that they are independent, well, that has consequences for the distribution of the yi's, right? So the yi's are going to be normal as well, and the expected value of yi will be just beta 0 plus beta 1 times xi minus x bar, right? Because the expected value of the error term is 0. Okay, so that's basically an assumption that the mean of our response variable y is well represented by a linear function. Okay, so that's one. here, of course, we have these assumptions about the error term, that it's normally distributed with mean 0 with variance sigma square. That sigma square is constant, and it doesn't depend on the values of the predictor variable x. Okay, so there you are. Those are the assumptions. Okay, now let me remind you that we already know what the estimators for beta 0 and beta 1 are, right? So let's write them down. Our estimators, beta hat 0, we know that if we are dealing with the centered model, we can show, for instance, using the normal equations approach, that the estimator, the least squares estimator for beta hat 0 would be just y bar, meaning the sample mean. Okay, so let me just write this down, because I want you to see something here. Note that this guy, right, y bar, is a linear combination of our y's. Okay, that's important. Again, we have already seen what the estimator for beta 1 for the slope would be, and it would be just the following ratio. It would be the summation of xi minus x bar times yi divided by, you know, sxx, right? Sometimes is called that sum of the xi's minus x bar squared. That's another way of referring to that sum I just wrote down. Okay, so again, this guy, well, we know, and we have done it when we discussed the distribution of beta 1 hat. We can rewrite it as a linear combination of the yi's. Okay, and these ci's, these coefficients that multiply the ith response variable, well, that ci is going to be given by xi minus x bar divided by sxx, right? So where ci is that quantity we just said, right? The ratio between xi minus x bar divided by sxx, because this guy is sxx. Okay. Well, so that's kind of a summary of what we know about this centered model up to this point, thus far. So, but now, suppose that we wish to make an inference about a linear function of our parameters. Okay, so linear function of our parameters. Linear function of our parameters. So, as the name suggests, this is just going to be a linear combination of beta 0 and beta 1. Let me write that down as follows. A 0 multiplies beta 0 plus a 1 that multiplies beta 1. So that's what we mean by a linear combination of our parameters. In a sec, I'm going to give you an example of a linear function of our parameters that could be something we might be interested in. Okay, so let me find, we want theta where do we have theta? Okay. No, that's not theta. Let me find it. Okay, there we are. Okay, so example of a linear function of our parameters that could be something we might be interested in. Let example let a0 be 1 and we're going to set a1 equal to just xi minus x bar. That could be interesting, and I'll show you why. Right? If we do that, right, we end up with a0 times beta 0, that's just beta 0, and a1 times beta 1 would be xi minus x bar times beta 1, right? So let me write it down here. In that case, what we end up with is just beta 0 and beta 1 times xi minus x bar. But if we go back to our assumptions, guess what? That's a linear function of our parameters, right? It's the expected value of yi. So can you see that we might be interested in such functions of our parameters? Okay. So let's keep going. At this point, we have established that it's a good idea to study these linear functions. Okay. Well, these are parameters, so theta is going to be a function of those parameters, right? So we are going to try and estimate this guy somehow. We have already shown that beta 0, beta hat 0 and beta hat 1 are the ones that we have here, are least squares estimators of beta 0 and beta 1 respectively. But we have also shown that in the particular case of linear regression, least squares estimates for beta 0 and beta 1 are also maximum likelihood estimates, right? And by the invariance property of MLEs, right, maximum likelihood estimators, we know that if we want to estimate a function of, a maximum likelihood estimator, then we just apply that function. So what I'm trying to do is justify that a good idea, a good estimator for that quantity theta that we are interested in is going to be just theta hat equals a linear combination of our estimators for beta 0 and beta 1. Make sense? And this is just by the an argument would be by the invariance property of MLEs, because our least squares estimators of beta 0 and beta 1 are also maximum likelihood estimators. Okay, so that's a good idea by the invariance property. Let's keep going. Something else that we have done in the past is that once we have an estimator, for instance, we did this in detail for beta 1 hat. Once we had an estimator, we wanted to study its distribution, right? So, as we already said, right, beta 0 and beta 1 are a linear combination of the y's, and the y's have a normal distribution because of our assumptions about the error terms, about the epsilons. So it turns out that theta hat will also be a linear combination of normals. Therefore, the distribution of theta hat will also be normal. And we know that normal distributions need two parameters to be fully specified: the mean and the variance. Okay, so let's find the expected value of theta hat. So expected value of theta hat. This is the same as the expected value of that linear function. Now from statistics 256, right, if we want the expected value of a sum, that is the same as the sum of expected values. And that's by if we are talking to one of our mathematician friends, is because the expected value is linear. Okay, so we have that, and then we have a constant times random variable, right? So we get to factor out that constant. Let's do that. Let's factor out that a0 and that a1. We're going to be doing the same. Let's pull that guy out. Now the expected value of beta hat 0 happens to be beta 0. Okay, you can show that from the way that beta hat 0 is defined for the centered model. You can easily show that the expected value of beta hat 0 is beta 0. And you already know, right? We did that together. We did it in detail. That the expected value of beta 1 hat is beta 1. But guess what? A times beta 0 plus A1 times beta 1, that happens to be your target, theta. So the expected value of theta hat is theta. That's what you have shown here, which means that this estimator of yours is an unbiased estimator. Right? Okay. And that, well, happens to be the mean of the normal that we're interested in here. That's going to be useful for the distribution of theta hat. Okay? Okay. Now, let's find the variance of theta hat. Let me be lazy here. I will borrow that expression from what we just did for the expected value. So the variance is going to be the variance of a sum, right? Now, in general, we know that the variance of a sum is the sum of variances plus we have to take into account the covariances as well, right? So in this case we would have variance of this guy plus variance of this guy plus 2 times the covariance between those two terms that we have here, a0 times beta 0 hat, a1 times beta hat 1. Okay, let's write that down. So this would be this. Sum of those variances plus 2 times the covariance between these guys. Now, and this is where we realize that it was a good idea to do this using the centered model, the one that we're considering here, right? Because it turns out that if you are considering the centered model, then these are your estimators for beta hat 0 and beta hat 1, right? And you can show, remember it was one of our homework problems, if you compute the covariance between these guys, the covariance is 0. Okay, so, and also by properties of variance and covariance, let me simplify this a bit more. This we know, when we factor out that constant, we have to square it. So it would be A0 square and A1 square here, and here we get to factor out these guys, because if you remember, covariance is a special kind of expected value, the expected value of basically a cross product between two random variables. Okay, anyway, so what we're going to say here is that we know that the covariance between these two guys, beta hat 0 and beta hat 1, is 0 in the case of the centered model. So this is going to simplify nicely. So we only have this. But now, you guys remember what's the variance of beta 1 hat? We have also shown that before, and that happens to be sigma square divided by SXX. Okay, so sigma square divided by SXX. And here we want the variance of beta hat 0. That one we can find very quickly, because it would be, hey, variance of beta hat 0. Oh, it's the variance of this guy. So we would have 1 over n square times the variance of the sum of yi's, right? And these yi's are independent, so the variance of a sum of independent random variables is the sum of variances. So we have n times sigma square divided by n square. We end up with only sigma square divided by n. Make sense? Okay. So that would be the variance of beta hat 0. Sigma square divided by n. Okay? As you can imagine, it would be a good idea factoring out those sigma square. Okay, so that's what we're going to be doing next. Let's rewrite this expression like this. Let me do just this. We're going to have a0 square divided by n plus a1 square divided by SXX the whole thing just multiplied by sigma square. Okay? Okay. So that would be the variance of theta hat. Let's find the standard deviation. That could be useful. So let me use the following notation for this. Would be using this notation would be the variance of theta hat. Okay, theta hat. Okay, so now let me find just the square root of that. That would be the standard deviation. Standard deviation, just square root of that quantity we just found. Okay, are we good? Okay, so let me just summarize what we have done so far. Theta hat is normally distributed because it's a linear combination of normals, right? There we are. Theta hat is normally distributed, right, with mean, the mean that we found, theta, right, and standard deviation, this guy, right? And you could factor it out. We're going to do that next. We could factor out, we know that the square root of sigma square, is sigma. So let's place that guy outside that sigma. Okay? Make sense? Are we good? Okay. Now, we have made good progress because what we're going to be doing next is finding the distribution of our test statistic, okay, and that test statistic will also help us find a formula for a confidence interval for a linear function of our parameters beta 0 and beta 1, right? And as an example of an interesting linear function of our parameters is the expected value of yi. Okay, so to do that we are going to see something that I prepared for you in our lecture notes. So let me look for it and I'll be right back. Okay, I'm back. So this comes from your lecture notes. Okay, so here I have the expression for the test statistic that you would need if you wanted to test the following. The null hypothesis is theta equals a particular value, theta naught, right? And depending, and you know this from statistics 260, right? That depending on the alternative, you are going to have a different expression for the p-value, right? But note that, let me remind you, I'm sure that you guys already know this, but let me remind you that there's a correspondence between the direction of the inequality that defines your alternative hypothesis and the direction of the inequality that defines your p-value. So if you want to test h0, h0, theta equals theta 0 against theta greater than theta 0, then note that the direction of that inequality matches with the direction of the p-value. You want to find the probability that a t distribution with n minus 2 degrees of freedom is greater or equal to your test statistic t star. Okay? Same goes for theta less than theta 0. Note that the direction goes, the same. It goes in the same direction. The inequality goes in the same direction, right? Okay. And if you have a two-tailed alternative, then you have this expression, right? So basically, you're taking into account these two possible cases. Okay. Anyway, so let's use what we have shown to justify that that t star, the expression that we have for t star, has a t distribution with n minus 2 degrees of freedom. So first, let me remind you that the definition of a t distribution is as follows. A t distribution is a ratio between two random variables. The numerator must be a normal, 0, 1, and then in the denominator you are going to be dividing, right, by the square root of a chi-square divided by its corresponding degrees of freedom. Okay? Okay. So let's do that. Let's try to justify that t star has that distribution. Okay, a t distribution with n minus 2 degrees of freedom. So anyway, let's start with the numerator that defines t star, or test statistic. So note that up to this point we have argued, we have basically shown that theta hat has a normal distribution with mean theta and standard deviation sigma times the square root of a0 square divided by n plus a1 square divided by sxx. Okay, so we need a normal 0, 1 in the numerator of the definition of a t distribution. So all we are going to be doing here is standardizing this guy, right? To standardize this guy, we just have to remove its mean, subtract its mean and divide by its standard deviation. So let's say that what we have here is theta hat minus theta divided by standard deviation of theta hat. But in this case, that is the same as having just, this guy, theta hat minus theta, divided by that expression. Okay. You guys agree? So finding the numerator wasn't that hard. Let's talk about the denominator. So in the denominator we need a square root of a chi-square with of a chi-square divided by its own degrees of freedom. Let's think about a quantity that has a chi-square distribution. Remember that at some point we talked about s square, right? And S squared was an unbiased estimator of sigma squared, right? And remember that it's just the sum of the squares of the residuals divided by n minus 2. We showed, right? We provided a proof that s squared, meaning the sum of the square residuals divided by n minus 2, is an unbiased estimator of sigma squared. Also, from our discussion about the orthogonality theorem and orthonormal bases, right? We were able to justify that the sum of the residuals square divided by sigma square has a chi-square distribution with n minus 2 degrees of freedom, right? So what we just said is here in one of our slides, our lecture notes here. This is what we just said. Oh yeah, we used W for that, for the sum of the squared residuals expressed in terms of the u's, where the u's were, an orthonormal basis for the residual space. Sigma square is just the variance of our epsilons, right? Okay, anyway, using the orthogonality theorem and our orthonormal basis approach, we argued that this quantity has a chi-square distribution with n minus 2 degrees of freedom. And as I said earlier, well, we showed that this is an unbiased estimator of sigma square, that S square is an unbiased estimator of sigma square. Okay, so we have that S square equals W divided by n minus 2, and we know that W divided by sigma square has a chi-square with n minus 2 degrees of freedom. Let's use that, okay? So S square, which is defined as W divided by n minus 2, note that what we know is that W divided by sigma square has a chi-square distribution. So let me multiply by n minus 2 here. N minus 2 times S square would be the same as W. Then if we divide both sides by sigma square, we know that that in turn will have a chi-square distribution, right? And actually we have that result from our textbook. This has a chi-square distribution, right? Let me see if I can find it. Chi-square with n minus 2 degrees of freedom. Okay? So it makes sense that our denominator will be this guy divided by its own degrees of freedom, the square root of that, right? So finally, our candidate for the denominator that is going to define our t distribution is this guy, but we need to divide that guy by its degrees of freedom, which is the same as multiplying by 1 over n minus 2, and what we need is the square root of the whole thing. That would be a good candidate for our denominator, the denominator that defines t star, right? So let's see if that works. So t star, let me write it down. We claim that it's a good idea to combine our ingredients. The numerator, we have it here. Let me copy and paste that expression here. Okay. Let me actually open another window here. Because we're going to need it. We're going to need some room. And let me copy and paste the denominator that we think is going to work. Okay? Make sense? Now, note, first simplification that we're seeing here. First, n minus 2, n minus 2. Okay? So this turns into s squared divided by sigma squared. The square root of that, right? So the square root of s squared divided by sigma squared is just going to be s divided by sigma. Okay? You guys agree? Okay. So instead of having all this, in the end, what we have is this, and then furthermore, just have s divided by sigma in the denominator, right? You guys agree? Because these guys, n minus 2, they cancel out. We have the square root of s squared, sigma squared. That's what we have below. And the square root of s squared divided by sigma squared, just s divided by sigma. Now, note that this is equivalent, when we do the algebra, to sigma times theta hat minus theta, right, divided by this. So which means that the sigmas will cancel out, and this guy will multiply this guy. So in the end, what we have is just, you know, the sigmas cancel out, and then we're going to have theta hat minus theta divided by s times that square root. Okay, so let me just copy this guy, only the one in the numerator, and modify that accordingly to what we just said. And again, let me repeat the argument. When we do the algebra, we're going to multiply sigma times theta hat minus theta, and then s multiplies sigma times square root of all this, right? But then the sigmas cancel out, and we only have s times the square root of a0 squared divided by n plus a1 squared divided by sxx. And then if, and that's what we're saying should work, So if I didn't make any mistakes, that should be the test statistic that we have in our lecture notes. And it is, right? Okay, so now we have this test statistic, right? Okay. From statistics 260, right, what we know is that we can use this quantity as a pivotal quantity, and that pivotal quantity is going to help us find the confidence interval for our parameter of interest. So let me remind you how we could use it to find a formula for a confidence interval, right? Okay, so we can use T star as a pivotal quantity. To find our CI, our confidence interval, for theta. Let me remind you what we mean by that. That we could take a couple of critical values from the distribution. We know that this guy has a t distribution with degrees of freedom n minus 2 degrees of freedom, right? So what we need is critical values from a t distribution with n minus 2 degrees of freedom. Depending on the confidence level that you want, those critical values will change. So in general, what we could do is the probability that this quantity t star lives between minus t of alpha divided by 2 and t of alpha divided by 2, where those guys are critical values from a t distribution with n minus 2 degrees of freedom, is 1 minus alpha, right? You have seen something before in statistics 260, right? Okay, and then what we can do is solving for theta. Well, for theta, yeah. What we end up with, right, is you're going to be multiplying, right, here, both sides of the inequality. Then you're going to be subtracting theta hat, both sides. You're going to be dividing by a negative. Then the directions of the inequalities will switch, and you're going to end up with something that looks like this, right? Theta hat plus minus, let me see, I think we have it here. Yeah, we have it here. T of alpha divided by 2 times this guy here, our denominator. Right, and that is going to give you 1 minus alpha times 100% confidence interval for theta, right? And I think that we also have an expression for that guy here in our lecture notes and in your textbook as well, right? So that's exactly what we got. Okay, and finally, as we said, right, if we let a0 be 1 and a1 be xi minus x bar, then this formula can be used to find a confidence interval for the expected value of, your response variable at a particular value of the predictor. Right? Makes sense? So I'm using x star here for a particular value of your predictor variable. Okay? Make sense? Okay, so let's summarize what we did here together. So what we did is we claimed at first that it would be a good idea to study linear functions of our parameters beta 0 and beta 1. An example was this, that the expected value of our response at a particular value of the predictor is given by a linear function of beta 0 and beta 1, the parameters of our model. So we considered the centered model because we anticipated that was going to help us to derive these results more easily. And that's because in the case of the centered model, the covariance between our estimators is 0, and that simplifies things a lot, right? And then we have combined what we have learned, what we have shown so far about our estimators of beta 0 and beta 1. We have used the distributional consequences of our assumptions of the random fluctuations, the epsilons. We have also used our knowledge about the expected value and variance of those estimators, beta hat 0 and beta 1 hat, and all that helped us to derive a test statistic, to carry out hypothesis tests, and also, well, this formula for a confidence interval. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.